I'm going to talk about section 16.4. It's pretty short in the book, but very important. And then go right into an example. So we're looking at absolute motion analysis, and that's basically saying that we can describe the motion completely if we know the angular rotation about a fixed line on the body or through the body, and the motion, so this would be a rotation, and the motion of a point on the body. Alright, if we can relate the angular rotation to a motion of the point, this would be the translation motion. We then get general planar motion. Right? General planar motion was a translation plus a rotation. So if we can relate, here's the goal, relate S to theta somehow. And I'm going to do an example right off the bat. We basically want S as a function of theta. To get this, we're probably going to have to use some geometry or trig. And in this case, we're going to use some trig. And then we can get the velocity, the relationship between v and omega as the first derivatives. And we can figure out the relationships between the acceleration and alpha by taking the second derivatives. Alright, velocity and acceleration. Okay, so I'm going to jump right into this problem where we have a cam. If you don't know what a cam is, it's not a perfect circle. It's oblonged a little bit, and the whole point is to move this in and out, something like a valve in your engine, to move back and forth as this rotates. So if your engine rotates faster, this is going to move back and forth in and out faster as well. So we can relate the motion of theta to the motion of B. Okay, so what we're doing is relating the rotational motion to rectilinear motion. And we're going to do that with a fixed point O. I'm going to use this point. And with this, we're going to find the velocity and the acceleration of the rod itself. So if we know alpha and we know omega for this cam, how fast it is rotating and the rate of change of its rotation, we can figure out how fast this rod is moving left and right horizontally in this case. So we can use a coordinate S to locate any point on the path. That S is going to be a function of theta, and then we can take derivatives. So let's do it. We want to find the velocity and acceleration of this rod right here. Well, let's make S as a function of theta. First, we can say, if we look at this triangle up here, if this is R and this is R, we're going to call this B, C, and D. This is the length R cosine theta if this is the angle theta. and that is the case here. So we can say S is equal to, and we're looking for any position S along this point. Would this be our fixed reference? S is going to be equal to 2 of these because there's another one, right? And R cosine theta there. 2R cosine thetas. We can take our first derivative. ds dt would be negative 2r, take the derivative, r sine theta. Don't forget the chain rule gives us the theta dot. Theta dot is equal to omega. We can rewrite ds dt as the velocity as negative 2r sine omega. And in this case, it's moving in the minus I direction. Okay, we just need to take another derivative now. The acceleration would be equal to the second derivative, or the first derivative of velocity, which we have now. And product rule and chain rule will give you a negative 2r times derivative of omega with respect to time, which is alpha, times the sine of theta minus 2r omega times the cosine of theta, and then chain rule multiplied by the time derivative on that term too. And this one is omega. So this ends up reducing to, well, acceleration equal to negative 2r alpha sine theta. And then we had an omega term right here, and this thing is omega right there. Let's put those together. We get a plus omega squared cosine theta. And that is also constrained to move in I direction. Alright, thank you.